Now we're looking at problem type 68, which involves finding factors of cubic functions. Now what we're tasked with doing is finding the factored form of f of x. Well, what we're going to find by going through this problem is that finding the factored form of f of x is going to involve the same steps we did to find the roots of f of x. Because remember, roots and factors are very interchangeable. Like for example, let's say we know that one of the factors of a polynomial is x minus 7. Well, then the root associated with that factor is x equals 7, right? You imagine setting the factor equals 0. What if the factor is x plus 3? Well, then that root would be x equals minus 3. Okay, so finding the factors, which is what we're trying to do this time, is just like finding the roots. It's different, just a very similar process. Okay. So like before, the first thing we did is we used rational root theorem to identify possibilities. Right? Now there's a couple things that jump out in terms of this example versus the previous example. Our p term is just 1. So our leading coefficient is just a 1. That's going to make it easier. And our q term, which is our constant, is 12, which is going to be a little easier to sort through than 48. So we're going to list all our factors of q, which is our constant term, over all our factors of p, which is our leading coefficient. All right, so we'll set up a fraction here. And let's see, we'll say all the factors of q are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay, not bad. Then we need the factors of our leading coefficient, which we call p. Now, fortunately, leading coefficient is just 1. So that means inside the denominator, we just have plus or minus 1. Well, that makes things pretty easy. So that just means that our factors are just plus or minus 1, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. What that means is when we go to start testing some possible roots, this gives us a list of ones that we would test. We wouldn't test anything that's not on this list, such as plus or minus 5. Because plus or minus 5, those are not possible rational roots of this polynomial. So we only want to test the ones that are possible. Okay? To see if they're actual roots, we're going to use remainder theorem like we did before. So we're going to test, for example, f of 1. We're going to evaluate f of 1 we're going to test x equals 1 by evaluating f of 1 and see if that gives us a remainder of 0 or if the value equals 0. So we're going to say this is equal to 1 cubed minus 6 times 1 squared plus 5 times 1 plus 12. Well, that's equal to 1 cubed is 1 minus 6 times 1 is 6 times 1 squared is 6. Let's see, plus 5 plus 12. So 1 minus 6 is negative 5, plus 5 is 0, and plus 12 is just equal to 12. Okay, so this doesn't equal 0. So x equals 1 is not one of our roots, meaning x minus 1 is not one of our factors. All right, so we test again. This time, the next one I typically test would be x equals negative 1. So we're going to let's say f of negative 1 is equal to negative 1 cubed minus 6 times negative 1 squared plus 5 times negative 1 plus 12. All right, that is equal to negative 1 cubed is just negative 1. Okay, that's then minus 6. So negative 1 squared is just positive 1, so minus 6, and then minus 5, then plus 12. So 1 minus 6 is negative 7, minus 5 is negative 12, plus 12 is equal to 0. Okay, good. So what we found is x equals negative 1 is one of the roots of that polynomial, meaning more importantly that x plus 1 is one of the factors. Okay, and just like we did before, now that we found one of the factors, we're going to use the reduced polynomial to find the other factor. So one of our roots or x-intercepts is x equals negative 1, but we're actually focused on, that doesn't look like a negative 1, x equals negative 1. In this case, we're focused on factors, which is x plus 1. Okay, so to set up our long division, we're going to say negative 1 in the box here. You put either the the c term or you put the root in the box. Then along the left here, or the right, we're going to put the coefficients. So we have a 1 and a -6 and a 5 and a 12. And start the synthetic division. We first start by just dropping the first term down, right? And then 1 times -1 is -1. -6 plus -1 is -7. -7 times -1 is 7. 5 plus 7 is 12. 12 times -1 is -12. And then 12 plus -12 is 0. Okay, good. We got a 0 for our remainder, which we expected, right, because we're dealing with one of our roots. More importantly, we now have our reduced polynomial. We have our quadratic, which would remain if we took this factor out of the original polynomial. Our quadratic is x squared minus 7x plus 12. Okay, that's good. And now we can factor this quadratic to get our remaining two factors. So we're going to, since the reduced polynomial is a quadratic, we can use our methods for solving quadratic equations to find the other two factors. So our quadratic is x squared minus 7x plus 12. And we're going to break that into thinking of two numbers that multiply to give positive 12 and add to give -7. That would be x minus 4 and x minus 3. Okay, so that means the factored form of f of x is, let's see, f of x is equal to the first factor we found, which was x plus 1, times x minus 4 times x minus 3. So that's the factored form. That's the factored form of the cubic. Okay, let me know if you have any questions, guys, and I'll talk to you soon.